All right, so now that we've discussed the concept of atoms and the subatomic particles, I'd like to get more in depth into chemical bonds. And to discuss this, we first need to kind of classify these bonds based upon various properties. So we have several different types of bonds that we spoke about. Technically, we have 5 types of chemical interactions. The first is nonpolar covalent bonds. The second is called polar covalent. The third is ionic. The fourth is going to be hydrogen bonds. And then we have van der Waals interactions. So let's talk about the 2 covalent bonds initially, nonpolar and polar. So remember what the word covalent literally translates to. Cooperate, or cooperative. Co means together, and valent is talking about the valence shells. In nonpolar and polar covalent bonds, literally you're going to see a sharing of the electrons. So in either case, you're going to see a sharing of the electrons. But the big difference is that in nonpolar covalent, you're going to share those electrons equally, while in polar covalent, you're going to share them unequally. Okay. So in either case, the atoms involved in these bonds are sharing electrons either equally or unequally to fill their valence shell. Because remember, these bonds arise from the scenario where atoms are attempting to fill their valence shells and become inert. Right? So for instance, if I have a hydrogen atom, which only has 1 electron in its first shell, and it engages in a covalent bond with another hydrogen atom, those electrons are going to be shared equally, halfway between both of those hydrogens. And if I were to look at the valence shells of these hydrogens, since it's the first shell, both of those hydrogens have 2 electrons in their valence shell, due to the fact that they're each contributing 1 electron. So I could literally draw that kind of like this, okay? Where they're effectively sharing those electrons, thereby filling each atom's valence shell. And those electrons are shared equally. Okay? So that is a nonpolar covalent bond. Okay? The electrons are shared equally between the 2 atoms. And those electrons are contributed by the atoms to make this shared pair. So every solid line you see represents a covalent bond. We don't necessarily know if it's nonpolar or polar, but that single line will tell you also that there are 2 electrons in that bond, 1 from each atom. So if it was a double covalent bond with 2 lines, technically there are 4 electrons that would be shared between the 2 atoms. Okay. With a polar covalent bond, the scenario arises where one of the 2 atoms has a stronger pull on electrons. So the electrons are still shared, but they're going to spend more time around one of the 2 atoms. For instance, here with oxygen and hydrogen. Now we know this is a covalent bond still because we have a solid line between the 2. Okay? And you're not always going to see these electrons. I'm drawing them so that you can actually see where they are, but typically you're only going to see the covalent bonds as solid lines. And we'll talk about in just a bit how you can determine if it's polar or non-polar. Right? So here I have this unequal distribution of electrons. Now, one of these electrons came from oxygen, but the other one came from hydrogen. So essentially what that means is oxygen has 1 additional negative charge from this electron, spending more time around that oxygen than around that hydrogen. And as a result, that extra electron brings with it a slight negative charge to the oxygen atom. And the absence of that electron brings with it a slight positive charge to the hydrogen involved. And the end result of this is our bond winds up having what are called poles. These poles are a negative or slight negative pole on the oxygen and a slight positive pole over here on the side of the hydrogen. So, no charge across the bond, neutral because there's equal sharing of electrons versus a slight negative and a slight positive charge. And this characteristic is going to be very important when we start talking about hydrogen bonds. All right. Next, ionic. In ionic bonds, electrons are transferred. So we have electron transfer from one atom to another, resulting in what are known as ions. So the example you were given in lecture was where sodium and chlorine engage in this particular type of bond. An electron is transferred from sodium to chlorine, and the end result of the reaction is you wind up with a sodium that now has one more proton than it does electrons, so it winds up being positively charged, and you have a chlorine ion called a chloride ion, which gained an electron and now has one more electron than it does protons, so it has a negative charge. These two ions are attracted to each other due to the difference in their charges, and that interaction between the oppositely charged ions is what we classify as the ionic bond. Furthermore, remember also that this sodium ion is classified as the cation in this instance, while this chloride ion is classified as the anion. And the easy way to remember that is anion stands for A negative ion. So A negative ion. If you can remember what the anion is, you can then, by process of elimination, figure out what the cation is. Okay? So, we have our anion and our cation. So these three bonds involve the transfer of electrons. These two bonds here, or these two interactions, do not. The hydrogen bond arises when we have two polar molecules, and one of those polar molecules, at the very least, contains hydrogen. So to have a hydrogen bond, you need to have hydrogen, and you need to have two polar molecules. These hydrogen bonds are commonly going to exist between the negative pole of one of the molecules. So in this case, let's say it's a water molecule. So I have slightly positive charges here on my hydrogens. I have a slight negative charge on my oxygen. If there's another water molecule that this one comes into contact with, this oxygen is going to be attracted to that hydrogen because they have opposing charges. Okay? Also, a way that you can always tell you're looking at a hydrogen bond is not just to look for hydrogen, which is one of the key requirements, but to also look for this dotted line. So if I have a polar molecule, I have a hydrogen, and I have a dotted line, that dotted line is the hydrogen bond. Now, these are weak bonds, but if utilized in large enough quantity, they can be incredibly powerful and strong. So that's a hydrogen bond. Which brings us to our final interaction, van der Waals forces. These forces, or interactions, are going to be brief, alterations of the charge around an atom due to electron orbit. So in other words, as we discussed in lecture, these electrons aren't static. They're not staying in place. They're constantly orbiting around the nucleus of these atoms. If at any one point in time there are more electrons on one side of the atom, that's going to result in a very slight negative charge on that side of the atom for a brief instant. At the same time, because those electrons predominantly are congregating on that side of the atom, on the opposite side, you'll have a slight positive charge due to the fact that you have protons in the atomic nucleus, and those protons have a positive charge which is not being neutralized by the presence of electrons on that side of the atom. So these electrons are orbiting around the atom, and as they do, they bring with them negative charges. So for a slight instant, one side of your atom at any point in time will have a slight negative charge, while one side might have a slight positive charge. And then as the electrons continue to orbit, those charges kind of switch around. If you have multiple atoms in close proximity to each other, the result of this is if one atom has a slight positive charge on the side that's facing the other atom, and that other atom has a slight negative charge facing this atom, they're going to be slightly attracted to one another. But then as the electrons orbit, they're going to lose that attraction and then be repelled. So these atoms are constantly moving back and forth, either attracted to one another or repelled from one another due to the orbit of the electrons. Okay? So these are very weak, very brief interactions, okay, that are due to these alterations of the charge around the atoms due to those electrons orbiting. Okay? So van der Waals interactions are the actual interactions that result from this brief alteration of the charge around an atom due to the position of the electrons around the nucleus. So these are the different types of interactions. These three are the only ones where we're actually looking at electrons being shared or transferred. And in the next lecture, I'm going to talk about how we can determine what type of bond is happening depending upon the atoms involved in that particular type of bond.